This little video is all about intermolecular forces. Right. So for the IB, you need to know, it's a standard level IB bonding topic, you need to know about intermolecular forces. And there's a number of people who are saying they're struggling with the concepts. So I'm going to go through those now and summarise them quite briefly. I'm not going to teach a full lesson on it, but just a summary to help with your revision. So you need to know intermolecular forces are things that happen between molecules. In other words, things that are simple covalent. So the word molecule refers to things that are simple covalent. Okay, which means they're going to be, largely speaking anyway, sort of non-metal atoms bonded together, like, for example, methane or HCl or CO2 or water, things like that. Okay, things made of non-metals typically. All right. And to be able to work out the intermolecular forces, you need to be able to draw decent Lewis structures and identify polarities of bonds and then polarities of molecules from that. So I'm not going to do that in this video. I'm just going to make sure that you're aware that you can't work out what the intermolecular forces are without knowing that. So you need to know about 4 types of intermolecular force. London forces, which are otherwise known as instantaneous dipole, induced dipole interactions. You've got to know about dipole induced dipole interactions. And you've got to know about dipole-dipole interactions. And you've got to know about hydrogen bonding. I'll come back to hydrogen bonding in a bit. These top 3 are all examples of what we call van der Waals forces. You're expected to know that term, van der Waals forces. All 3 of those fall under that category. So, London forces are the interaction between, you get this interaction between all molecules, but as electrons move around a molecule in, just moving around freely and randomly, at any one point in time, there might be an uneven distribution of those electrons. So just representing where the electrons might be, sort of distribution plot of where the electrons are. And for just a particular random point in time, there might be more electrons on the left than the right. We call that an instantaneous dipole. It just happens for a bit. Now, because there's a temporary dipole then, with electrons more on this side, it's slightly negative over here, that causes, or that delta plus there, causes electrons on a neighbouring molecule, which also might be non-polar, to be pulled slightly towards it, causing what we call an induced dipole. So the word induced dipole refers to the fact that it's been caused to have a dipole by the neighbouring molecule. So that's instantaneous and that's induced. Because this side of the molecule is delta plus and this delta negative, opposites attract, if you like. So we've got an electrostatic attraction, a very weak one between those 2 molecules, which might be non-polar. This same idea can happen between a molecule that's got a permanent dipole, due to the fact that within it there are polar bonds and the molecule is not symmetrical, so it's a polar molecule. An example might be HCl, so something like HCl would have that set up. Okay. That can cause an induced dipole and a neighbouring molecule. Neighbouring molecule could be non-polar, and there would be the fact that there's a permanent dipole here would pull these electrons in the non-polar molecule towards the delta positive, making again an induced dipole here, therefore making an attraction, a weak interaction between the dipole and the induced dipole, the molecule that maybe was non-polar. That's usually slightly stronger than a London force, but remember the London forces depend on the number of electrons, the size of the molecule, the amount of contact points between 2 molecules as well. Dipole-dipole interaction, when you've got two molecules, both with permanent dipoles. They could be the same molecule, they could be different molecules. Could be an example might be HCl. So delta minus, delta plus, delta minus, delta plus. These molecules have permanent dipoles because there's a difference in electronegativity between the two atoms. And therefore there's an attraction between the delta plus end of one molecule and the delta minus end of another. And so that's a dipole-dipole interaction. Typically that will be stronger than a induced dipole interaction and stronger than a London forces typically. Though as I say, London forces can be really strong if there's lots and lots of electrons. It's a very big molecule. None of those are anything like as strong as a hydrogen bond, which by the way is nothing like as strong as a covalent bond. So don't get the idea that these are anything like as strong as actual proper covalent bonding. But hydrogen bonding happens when you've got a hydrogen bond donor, and that would be an oxygen with a lone pair, nitrogen with a lone pair, fluorine with a lone pair. They are, hydrogen bond acceptors, Hydrogen bond acceptors. Hydrogen bond acceptors are things that can accept a hydrogen from a hydrogen bond donor, which I'll draw in a minute. And it's the lone pair that does that. So when we're drawing these, we must draw the lone pair in them and show the lone pair doing some work. To make a hydrogen bond, you've got to have a hydrogen bond donor as well, and that would be a hydrogen attached to an oxygen. It's a hydrogen bond donor because it's extremely polar, this bond. It's extremely polar because O, N and F have very, very high electronegativities, which is why those things are involved in these interactions. Or it could be HF, okay? Oops, delta plus, okay? Well, no, there we go. So, to show the attraction between, or the hydrogen bonding, we must draw the molecules, showing dipoles, showing lone pairs. Now I'm going to show you a way of drawing this between two molecules that are not the same. You could draw it between two water molecules. You could draw it between two molecules that are not the same. So ammonia dissolves in water, makes interactions with water as a hydrogen bond between the between the lone pair and the delta plus hydrogen bond donor. So I've drawn the polarities. I've drawn a dotted line between the N and the H, but I've made sure the lone pair is on that nitrogen between the nitrogen and the hydrogen. So that's that one. You could also draw a hydrogen bond between the hydrogen that's attached to the nitrogen, make that the hydrogen bond donor this time, and a molecule of water. I've only drawn one of the lone pairs, so it's only one of them that's doing the work. Okay, delta minus. So that's how you would draw them. Remember, with a really strong piece of evidence with hydrogen bonding, is a graph, then it's worth looking in the textbook. I'm not going to draw this perfectly now, but if you look at the hydrides of, say, group 6, so the hydrides of group 6 are H2O, H2S, H2Se for selenium, H2 tellurium. You'd expect, if the biggest factor here was the London force strength between them, for the boiling points to increase as the molecules get bigger. And for the last three of those, they do. So boiling points increase as you go down the group. So boiling points increase as you go down group 6 hydrides. But water's got a freakishly high boiling point compared to the others because it can make hydrogen bonds with other water molecules. And this trend, this same sort of pattern happens with the hydrides of group 5 and group 7 as well. And you'll see that in your textbooks. It's worth being aware of. So that's boiling point in degree C. And this is H2O, H2S, H2Se, and H2Te. Worth also highlighting that water, because it's got 2 lone pairs and 2 hydrogen bond donors, that water has an even higher boiling point than ammonia, which is similar in size and shape, similar in size and can make hydrogen bonds. But because water's got a second lone pair and got 2 hydrogen bond donors, it can make this really quite complex network of hydrogen bonds, which gives it a very high boiling point for its size. That's it. I hope that was useful. Let me know if you need any more help. Cheers.